Okay, on this, the last day of the unit, we're going to talk about continuity. Continuity is probably a concept you know of, and you probably think of it as I can draw it without lifting my pencil off the paper. But we're going to be a little bit more precise here. So for a function to be continuous at a, we're going to break this down into three conditions we need to sort of understand and follow. Okay, condition number one is going to be that the limit as x approaches a of the function exists. So remember, this in itself is two things, right? That means the limit from the left and the limit from the right both have to exist and have to be the same. But we're going to say that the limit exists. So far we're drawing a picture that kind of looks like this. We have a limit. Then the second condition is that f of a has to exist. So we're going to have an output at that particular point. And the last condition is they be equal. I need these two things to be equal to each other. So I have a limit, it approaches something. I have a value at that point, and I need to make sure that the value that I provide fills in the spot that the limit was going towards. And this is what's going to force continuity. So again, limit exists, the functional value exists, so there's no open hole, there is a place, and those two things happen to be equal. So, for what values of x is the function shown not continuous, describe them as what types of discontinuities they are, and then use statements to talk about them. So the first discontinuity occurs at x equals -2, x equals -2. This would be an asymptote or an infinite discontinuity, and describing it with limit statements would be like saying the limit as x goes towards -2 from the left of this particular function is infinite, as you can see in the picture, or the limit as x goes towards -2 from the right of the f of x seems to be some kind of negative infinity. So it's an infinite discontinuity if it's flying off towards infinity on one of the sides. Notice that this would not have a limit. Right? There's no limit. F of a doesn't exist, right? There's no way there's anything going to be equal. The next discontinuity is at x equals -1. And for x equals -1, we can see that the picture jumps from one branch to the other. So this is what we in general call jump discontinuity. A jump discontinuity. And for this type of example, the limit justification for this would be, well, the limit as x approaches, in this case, -1 from the left would be, let's see, it's going towards -2, and the limit as x approaches -1 from the right, we can see, is going down to 4. And so we have two different limits from either side, and so the violation of the definition of continuity here is that the limit doesn't exist. It's different values from either side. Now, for the third example at 1, x equals 1, this one is what we call a removable discontinuity. It is a discontinuity, but it's removable because the limit actually exists, right? The limit as x approaches 1 of f of x is, well, it's approaching this number right here, and it doesn't matter which side we're coming in from, so limit of f of x as x approaches 1 is equal to 1, but because of the open dot, we're violating condition number 2, right? We do not have an actual output of the function. And finally, x equals 2 is also a removable discontinuity, because, again, we have a limit as x approaches 2 of the f of x does exist, and it's equal to 4, but we also have an f of 2, which is visibly equal to -1, and so we have a limit existing, we have a functional value existing, but they don't be equal. So here we have no functional value, jump discontinuity. We have a functional value, but we don't have a limit. Removable discontinuities, generally we have a limit, but we either don't have a functional value or we have a functional value that is different. And these are really the four main cases we can fall into. So here's an example. Let's sketch a graph of this function. We'll label all intercepts, asymptotes, and discontinuities. I guess I'll have to shrink this one a bit because it's a little large. Okay, so for the x's that are bigger than or equal to 0, let's first plug in the number 0 to get an intercept. That's going to provide 2 over negative 1, which is a negative 2. And then we have this function is an x plus 2 over an x minus 1, x plus 1. So we have a vertical asymptote that is occurring at x equals 1. So let's go x equals 1 right there. Gives me a vertical asymptote. And then let's make a quick little number line. So I only need to know what it is bigger than 0. So I'll put the 0 boundary there. There's our 1. And then I can see that if I stick in numbers that go off towards infinity, I get plus, plus, plus. And then that's a multiplicity 1. So it looks like it's going to be negative on this side. And then over here, it's always got to be positive. And the 1, 0 is at x equals negative 2, which is not part of this graph. I can also see there's a horizontal asymptote, right? Horizontal asymptote at 0. So that means on this side, it must be doing something like this. Now, for the rest of the function, for the x is less than 0, on the negative side, I can see the top is x plus 3 and x plus 4. And on the denominator, I have x plus 3 and x minus 1. So there, I can see that I'm getting a asymptote at 1, but I don't care about that because that's not part of less than 0. I'm getting an x-intercept at negative 4, so 1, 2, 3, 4. I'm getting an x-intercept there. I'm getting a hole when I plug in negative 3. Negative 3 would provide 1 over negative 4. So I'm getting a hole that's happening at negative 3, comma, negative 1 over 4. So I'm going to put a little hole in there. And I'm getting an asymptote, a horizontal asymptote of y equals 1. That's the end behavior here. So there's this piece that's giving me an asymptote of y equals 1. And so it appears as though this graph seems to be coming upwards like this, through the hole, and then what's happening there? Let's plug in 0. As I plug in 0, it looks like I get negative 4. 1, 2, 3, 4. So that means that it's probably doing something like that. Okay, that's part A. I've labeled intercepts on the x-axis, negative 4, comma 0. I've labeled intercepts on the y-axis, 0, comma negative 2. I've labeled the asymptotes as y equals 1 and x equals 1. And I can see the discontinuities. So let's identify those discontinuities now. We have a discontinuity that is occurring at negative 3. So x equals negative 3 is a removable discontinuity since the limit as x approaches negative 3 of f of x is the limit as x approaches negative 3 of x plus 4 over x minus 1, which is equal to, I can see that when I plug in negative 3, I get 1 over negative 4. That's what I did when I did my whole analysis. So limit exists, so it's definitely removable if it was discontinuous, and I can see that there is no value at negative 3. So f of negative 3 is an undefined value. Let's say it doesn't exist because there is no input, or there's no output at negative 3. The next discontinuity happens at 0. X equals 0, jumps branches. So this is a jump discontinuity. Jump discontinuity. I can see that it's a jump discontinuity because the limit of f as x approaches 0 from the left would mean that I'm coming in on this branch right here, and if I plug in 0, I get 12 over negative 3, which is negative 4. And as I approach from the right, limit as x approaches 0 from the right means I'm coming in along the top branch, which is a 2 over a negative 1, which is a negative 2. and those limits are different. These limits are different. So this violates continuity because I don't have a limit. Finally, at 1, we have an infinite discontinuity. X equals 1 is an infinite discontinuity. Why is it infinite discontinuity? It's because the limit as x approaches either side, let's just say x approaches 1 from the right of f of x, means that I'm coming in along this guy, which means it would be a 3 over 0 vertical asymptote plus or minus infinity. And I already made my number line, and I saw that it was plus, so that means it equals positive infinity. And if you equal an infinite limit, if your output is infinite, or if you're tending towards infinity, this is a vertical asymptote. So those are the answers to part B. Then when I do part C, find the equations of vertical asymptotes and horizontal asymptotes. I already did the justification for the vertical asymptote. The vertical asymptote is x equals 1, since, let's do the other side now, the limit as x approaches 1 from the left of f would be, let's see, I'm doing this thing right here, still. It is still approaching 1, so I get a 3 over 0, which is a vertical asymptote, and the number line tells me that it's going towards negative infinity, and if you're negative infinity, you're a vertical asymptote. And for the horizontal asymptote, as I go towards the left, I can see that I'm using the bottom object, and so the horizontal limit is limit as x goes towards negative infinity of f is going to be dominant behavior. It's going to be limit of x squared over x squared as x goes towards negative infinity, which is 1. And I guess I'll have to scroll down a bit. I was hoping to fit it here, but I won't be able to do it. Limit as x approaches positive infinity of f happens to be the limit as x approaches positive infinity of top dominant is x, bottom dominant is x squared, x over x squared, bottom heavy, and I can see that there is an asymptote at y equals 0. So there's one of them, and there is the other one. That means I forgot to label my horizontal asymptote. Y equals 0, y equals 1. There's my vertical asymptote, x equals 1. Let's find a value of k that is going to make this thing be continuous. So right now I don't know if it's continuous. I'm going to force it to be continuous. And I already know that I can plug in 1 because this condition says x less than or equal to 1. And I can see then that f of 1 is going to be 1 squared, which is 1. So I just need to make sure the limit exists. So what is the limit as x approaches 1 from the left of f? Well, that would mean that I'm following the top rule. And so the top rule, this would become the limit as x approaches 1 from the left of x squared, which is 1 squared, which is 1. But then as I approach from the right, limit as x approaches 1 plus, means I'm going to be following the bottom rule, and the bottom rule, x approaches 1 plus, means I need to take the limit of sine kx, which is going to be, let's say I plug in x equals 1, and I get sine of k. So in other words, I need sine of k to be equal to 1. I need to make sure that the right-hand limit is the same as the left-hand limit. So when does sine of k equal 1? Well, that'll happen when k equals top of the circle or any number of cycles of that. So the correct answer here is that k can be pi over 2 plus 2 pi k for any k and z. Okay, one then here, let's do a find a value of the functions. Find the values of the constants that will make this become continuous. Now I have two different sides to perform. Limit as x approaches negative 1 from the left of f of x would mean that I'm following the bottom function, which would be 2 times negative 1 cubed plus negative 1 plus 7. That's going to be, let's see, negative 1 cubed is negative 1, times 2 is negative 2, minus 1 is negative 3, and plus 7 is 4. Limit as x approaches negative 1 from the right means I'll now be in this middle interval, and so there, if I plug in x equals 1, I'll get m times 1 plus 1, sorry, negative 1. So negative 1 plus 1 is 0. 0 times m is 0, and so I get a k. So those are convenient. In order to make my limit approach or work from negative 1, I just need k to be equal to 4. Now I also have to make this work at 2, so if I take a limit as x approaches 2 from the left, coming in just a little bit less than 2, so that would give me here m times 2 plus 1. 2 plus 1 is 3, so I get a 3m plus k. Limit as x approaches 2 from the right. As I approach from the right, that means I'm coming in bigger than 2. 2 squared 4 plus 5 is 9. So bringing these together means I need 3m plus k to be equal to 9. System of equations, but I already found that k equals 4. 3m plus 4 equals 9. 3m equals 5. And so it looks like m needs to be 5 over 3. So these two constants will make sure that the function is continuous overall. To end this unit, I'm going to remind you of a theorem that's extremely important, and we're going to use it all the time in calculus. If a function f is continuous on an interval a to b, then the function takes on all values between the minimum and maximum of f. Okay, this is kind of a weird one to say, but let's just draw a little sketch because it'll make it really super obvious. So if I have some kind of interval, let's say from a to b, and I were to graph some kind of crazy function, what this theorem is saying is that if you go to the absolute maximum, in this case right there, and you go to the absolute minimum, which is right here, then this function, as long as it's continuous and I can't lift, or I'm not allowed to lift my pencil off the paper, I must hit every single output in between those two values. So as I go up and down, I keep on hitting. I can hit any one of the outputs between the max and the min. So how can we actually use this as a real example? Let's use this intermediate value theorem to show that this equation has at least one solution. At least one solution. So notice f of x equals x cubed plus x squared minus 2x is continuous, right? It's a polynomial. Polynomials are continuous everywhere. Also, f of 0 is equal to, let's go plug it in, 0 cubed is 0, 0 squared is 0, minus 2 times 0 is 0. So f of 0 is 0, and f of, let's plug in 1, f of 1 is 1, plus 1 is 2, minus 2 is 0. That's still 0. That's no good. What if I stick in the number 2? 2 cubed is 8, 2 squared is 4. This is going to be big enough. Notice f of 2 is 8, plus 4 is 12, minus 4 is 8. So f of 0 is 2. When I stick in 0, I get 2. When I stick in 2, I get 1, 2, 3, 4, 5, 6, 7, 8. And so, can you guarantee me that I hit 1? The answer is, yeah. If f of 2 is, sorry, I put the wrong spot there. F of 0 is 0, and f of 2 is 8, then I have to hit 1, right? I might hit 1 more than once, but I'm guaranteed to hit 1 at least once. So, by intermediate value theorem, there must be a value of c, let's say, a c between 0 and 2, I don't know where it is exactly, but it's somewhere between 0 and 2, such that f of c is equal to any output that I want between 0 and 8. In particular, it's equal to 1. In other words, c cubed plus c squared minus 2c would be equal to 1, which is exactly what we wanted. So that is MWO for life.